All right, so now we're going to discuss the notion of a canonical divergence. So previously we had mentioned that if you were given a divergence function, you could induce a Riemannian metric and a pair of dual affine connections. So the question is essentially the inverse problem. If I give you a Riemannian metric and a dual pair of affine connections, is there a way to find a connection? It's like which induces, it's like those objects, okay? And we refer to such a divergence function, it's like as a canonical divergence, okay? So again, this is the topic of canonical divergences. In dually flat manifolds. Okay, so as I said, it's like we have seen that given a divergence function, right, we can obtain a Riemannian metric and a pair, a dual pair of affine connections. Okay, so so the question is, given a metric, a Riemannian metric, and a dual pair of affine connections, can we find a divergence function which induces that? Induces these structures. Sort of given geometric structures. Okay, so whenever you have this kind of problem, it's like the natural question to ask is the existence question. Does there exist such a divergence function? As well as the uniqueness question. Are there more than one divergence functions which satisfy this property? Okay. All right, so with regards to the uniqueness question, all right, so with regards to the question of uniqueness, right, it should be observed that there can be many divergence functions which induce the same dual structure. So many divergence functions induce the same dual structure. And that perhaps shouldn't come as such a large surprise, right? Because you know, previously when we talked about given the divergence function, how you construct these sort of Riemannian metrics, it's like a sort of pair of affine connections. We saw that it involved, you know, double and triple derivatives. It's like of the divergence function evaluated along the diagonal. So what that's basically telling you is that you know, it's like the way in which a divergence function induces it's like a Riemannian metric and a pair of affine connections, relies just on local information about the divergence function. Okay, so you might expect that it's like that gives you some flexibility to it's like to have multiple divergence functions which satisfy this property. Okay, so the reason for this is that okay, so this is because the dual structure only depends sort of locally on the behavior of the divergence function, but locally in what sense, right? See, the divergence function is defined on 2 points. It's like on the manifold. And as I said, it's like you evaluate these derivatives, it's like the divergence function, along the diagonal, basically. So you're basically looking at a neighborhood of the diagonal of 2 copies of the information manifold. So the dual structure depends locally, only depends locally, it's like on the sort of divergence function in the neighborhood of the diagonal, right? Right. Another way to sort of naively think about this is that if I were to only specify for you, the first few derivatives of a function, then you only know the first couple of terms. It's like in a Taylor expansion of the function, right? So you have no insight as to what happens for the higher order terms, all right? And obviously, if you have different higher order terms, you have different functions, right? So again, morally, you can sort of think of it in that way. Okay. So, so how do we see it? So we're going to see it basically by saying that, well, okay, you can shift the divergence function by some other function as long as that other function has, again, these second order derivatives which show up in the definition of the Riemannian metric and the affine connection, which vanish on the diagonal, right? So let's try to be a bit more precise about this. All right, so, okay, so the longer answer to this is that, okay, so given some divergence function which depends on 2 points, right, we can sort of add a term, let's call that little d of cos C prime. Well, let me just put a comma there, right? Without changing the dual structure, right? So long as, well, so I should say a non-negative term, right? So the function has to be non-negative, all right? But it's a non-negative term. It's like, okay, so given an original divergence function, I can add essentially a perturbation. It's like a non-negative perturbation without changing the dual structure, so long as the derivatives, it's like, well, the first thing is that it has to vanish. It's like along the diagonal, right? And then it's, it's like various, it's like first, second, and third partial derivatives have to vanish as well, right? Okay, so if I differentiate respect to the first variable and evaluate along diagonal, it vanishes. If I differentiate respect to the second variable and I evaluate along the diagonal, it vanishes. And sort of the same sort of high order thing. And then as well as the third derivative, but the third derivative has to be this kind of mixed object, right? Okay. All right, so I should mention a bit of notation. It's like the partial prime term just means that I'm differentiating respect to the ith component of the second variable, right? And the same thing is here. So here I have differentiation respect to I and j of the first component, of the first slot, and then respect to k of the second slot, respect to I and j of the second slot, respect to k in the first slot, right? So, all right, it's not so surprising, right? So if you have this divergence function and you shift it, it's like by this object, which is non-negative, in the following way, where this sort of perturbation satisfies these sort of vanishing derivative conditions, then it shouldn't surprise you that the divergence function, the dual sort of geometric structure, which is induced, it's like by the perturbation, it's like of the original divergence function agrees with the sort of dual structure induced by the original divergence function. Okay, so that's sort of, it just follows, if you will, it's like from the definition of how you get the Riemannian metric and this dual pair affine connections given a divergence function. All right. So what is perhaps interesting is that if, on the other hand, you're on a dually flat manifold, then there is some sense in which you have a unique canonical divergence. So let's try to address this more carefully. Okay. So, but on a dually flat manifold, right, we can obtain a unique canonical divergence. Okay, and I should say that it's unique up to affine transformations. Up to affine transformations. Okay. So the way we're going to proceed basically is that we're going to essentially show that this canonical divergence for a dually flat manifold is really coming from a particular Bregman divergence, which is associated, as we all know, it's like with some appropriate choice of a convex function on this. So the way we're going to try to then construct this sort of canonical divergence is, as you might expect, by first constructing this convex function. Okay, so let me state the following lemma. So if M is dually flat, right? Then there are a pair of dual coordinate systems. Sort of theta and eta, and a pair of sort of Legendre dual convex functions. Phi, theta, and psi eta, right, satisfying the property that this is equal to 0. Okay, and the metric is given by Gij theta is equal to partial respect to I, partial respect to j, phi theta, and then G super ij on the dual coordinates eta is equal to partial respect to I, partial respect to j of psi eta. Right, and then if you recall, the reason why you had subscripts in one case and superscripts in the other case was because the tangent spaces, you know, it's like to the information manifold, are can be you can construct a basis for it. It's like either in terms of the, you know, it's like the ones induced by the coordinates associated with theta or the ones associated with eta, and they're dual to each other. It's like in the sense which you talked about, which is to say that they have this auto sort of normality relationship, right? So they, you know, it's like when you pair, it's like a primal basis element with a dual basis element. It's like they give you the Canonical delta, right? So well, so maybe pair is the bad way of taking, but you take the inner Riemannian inner product of that thing, you have that property, and it turns out that that's those two things are related by this raising and lowering operator via the metric. So that's the reason why you have these lowered and raised indices here. Okay, anyway, so that's how you can get the metric. It's like, and then the cubic tensor okay, is given by Tijk theta, right, as partial I, partial j, partial k of, again, the convex function, or 2t super I j k in the dual coordinates is partial super I, partial super j, partial super k of the dual convex function. All right, and again, let me sort of remind you that if you have a Riemannian metric, you can induce the Levi-Civita connection, and then what the cubic tensor does is to tell you how the dual pair of affine connections is perturbed from the Levi-Civita connection. So this, so the cubic tensor shifts. It's like the Levi-Civita connection. It's like to give you, it's like these dual pair of affine connections. Okay, all right. And in some parts of the literature refer to this cubic tensor as a skewness tensor. And the reason why Amari, it's like, avoids referring to this as a skewness tensor is because this tensor is actually symmetric. Okay, all right, anyhow. Okay, so that's the lemma. And essentially the idea is to start with this idea of the manifold being dually flat. Okay, and what that basically means is that in one of the coordinate systems, right, say the primal one, the connection coefficients vanish. That's what it means for something to be flat. with respect to some coordinates is that the connection coefficients vanish. And if you recall, when the connection coefficients vanish, it's like then the usual notions of derivatives agree with the covariant derivatives. So that's the basic tool which then allows you to start building up this convex function. Okay, so let's try to do that a bit more explicitly now. Okay. So let me just mark that off here, and then we'll have to keep erasing it in order to develop the rest of the proof. Okay, so the proof is as follows, right? So we start with an affine coordinate system. Theta, which we know it's like is there because we assume that M is dually flat, for which this connection coefficients gamma ij k theta equals to 0, right? So from this, right, so what we do then is that we use the definition of metric compatibility, which I would say dual metric compatibility, right? If you recall, what that is saying is that you have a vector v and w, and you parallel transport it by one of the connections and parallel transport it by the other one, that you have this invariance, it's like of the inner product. Okay, so we use the definition of dual metric compatibility, which in coordinates, right, that the partial respect to I of Gij, oh sorry, Gjk is equal to gamma ijk plus gamma star ikj. Right. Okay, so that's the local coordinate representation. It's like of this dual metric compatibility condition. Okay, but we know that in this theta coordinate system, it's like the connection coefficients of the primal affine connection vanish, so this term vanishes. And you're just left with gamma star ikj. Okay. Then the other thing we observe is that the connections are symmetric. So we use the fact the connections are symmetric. And what that implies is that the partial of I g j k is equal to the partial of k g j I. Okay, so what's basically happening is that you have this identity with a bunch of dummy variables I, j, and k, right? But you know that this dual affine connection, right, is symmetric under an interchange between I and k, right? So if you interchange these things, right, so this is equal to gamma Kij star, right? But if you change k and I here, you get partial respect to k of Gji, which is the equation which I have here. Okay, so this part is just due to symmetry. And then this identity is just the same as this original identity, but with the change of the dummy variables. Okay, so anyway, so this, by using this factor, it's like we have this equality, okay? And then more or less, it's like what happens then is that because of this equality, you can essentially construct your convex functional, right? So so how do we do this? Okay. So we can fix one of the indices, and then I just denote it by a dot. Okay. So, all right, so we have the partial of I, G, K dot is equal to partial respect to K of G, I dot. Okay. Right, so then what happens is that I can find a function phi, which satisfies the property that G sub I, which is the partial, is given like this. Okay, there's a dot here, right? So, or for each j, we have that G ij is equal to partial I psi j. Okay, but the other thing, of course, is that a Riemannian metric tensor is symmetric, right? Which basically means that partial I psi j, right, is equal to partial j psi I. All right, and what happens is that this is an integrability condition, which then guarantees that there is actually a function which I can integrate out. So this implies that there exists phi such that phi sub j is equal to partial respect to j. Okay. And then this implies that this Gij is just this mixed partial of psi. And this is convex, since the Gij is part of a matrix which is positive definite. All right, and then finally, it's like we use the fact that the covariant derivative and the usual partial derivatives agree with each other because the connection coefficients vanish, right? So nabla sub I is equal to partial sub I for the theta coordinates, since gamma ijk theta equals to 0. So this skewness tensor Tijk then becomes partial respect to I, partial respect to J, partial respect to K of this convex function. All right, so this gives you this primal convex function. You can do essentially the same construction on the dual coordinate system using the fact that it's like the dual connection coefficients vanish. It's like with respect to the dual coordinate system. And then finally, of course, you have to show that these two things are related to each other via the usual Legendre transform. Okay, but that's essentially the idea. Okay, so similarly, for the dual convex functions, psi eta, and sort of we still need to show they're related by Legendre transforms. Okay. All right. So that's sort of the first part. All right. And the second part, as you might expect, is that now you have these convex functions. You can look at their corresponding Bregman divergence, right? Okay. So let's go ahead and do that. So this is the theorem, right? So when n is dually flat, right, there exists the Legendre pair of convex functions, which is sort of the statement of the lemma. And the canonical divergence. Divergence given by the Bregman divergence. Okay, so the Bregman divergence between 2 points is this sum of the convex functions. One is the primal convex function with respect to the primal coordinate of the first variable, and the dual convex function with respect to the dual coordinate of the second position. All right, and then there's this inner product that's like between the two, one in the primal representation, one in the dual representation. So if you recall, it's like when we talked about the lemma, it's like there was this thing which looked suspicious like this, suspiciously like this, but that it was equal to 0. And the reason why it was equal to 0 was basically because we had the expression like this, but there wasn't a prime on the eta, right? So what they was basically saying is that, well, we had the theta and eta, but they were corresponding to the same point. So they were just primal and dual coordinates corresponding to the same point, which basically means that that combination which we saw in the previous lemma was the divergence evaluated on the diagonal, right, which, as we know, vanishes. So that was the reason why that particular expression vanished in the lemma above, was because it was just a divergence function of something along the diagonal. Okay, which, as we know, vanishes. So this is unique. So the remark is that this canonical divergence is unique up to affine transformations. And then conversely, the canonical divergence induces this original dually flat Riemannian structure, which we talked about. Okay. Okay, so let me state another theorem. Right, so the KL divergence is the canonical divergence of an exponential family. Of probability distributions which is invariant and dually flat. All right. So a lot of times, it's like the KL divergence is used without really much thought as to why it's the right structure. And the whole point of this discussion, if you will, is that in essence, the KL divergence shows up in these exponential families of probability distributions because this exponential family of probability distributions have a dually flat structure. Okay, and when they have this dually flat structure, it induces one of these canonical divergences. And as we recall, it's like as we see here, it's like that canonical divergence happens to be a Bregman divergence. And in particular, for this exponential family of probability distributions, that canonical divergence, that Bregman divergence which comes out of this, is the KL divergence. Okay, so there is a specific reason why the KL divergence shows up very, very naturally in this. Okay, and so one has to be, it's like aware in some sense as to why it is that certain choices of divergence functions are appropriate. And one way to sort of think about this again is that it is the it's basically the dually flat structure. It's like of this space of probability distributions which you're working with, which is inducing this very natural choice of divergence for this problem. All right, so let me just stop here for now.